Hi class, this video is on topic C5, thermal energy and heat capacity. And this is the beginning of a new chapter within our energy unit. The kinetic molecular theory is a theory of matter that states that all matter is made up of small, constantly moving particles that attract each other. And since they're in a state of constant motion, they have kinetic energy. So there's two types of energy associated with matter in KMT. So there is potential energy and kinetic energy. And this is, we're talking about on the small scale of the particles. So the particles contain potential energy due to the interactions between these particles. Particles, or they could be atoms or molecules. So the farther apart these particles are, the more potential energy they have. And why is that? Because recall that the KMT says that these particles attract each other. So if we hold them apart, there is some potential energy. So this is the less obvious one, I find. Kinetic energy, that's one that makes a little bit more sense initially to us. The kinetic energy of particles is due to random motion of particles. The faster motion makes the object, we would say that it's warmer, and the slower motion makes the object colder. So if we think of solids, liquids, and gases, KMT is used to explain why we have three states of matter. We have solids that the particles are closer together, so there's less potential, and then you have gas molecules, they're further apart, that they have more potential. And in addition to that comparison, in order to be a gas, a substance has to have more kinetic energy as well. So these particles are further apart, so they have more potential than these particles, and they also have more kinetic energy, so they're vibrating more quickly. Thermal energy is the sum of potential energy and kinetic energy possessed by the particles of a substance. So we say thermal energy is equal to kinetic energy plus potential energy. And thermal energy, just like the other forms of energy, is measured in joules. It's a scalar. And a hot object has more thermal energy than a cold object because the particles are moving faster. So if we're comparing a hot object and a cold object, that's maybe a mention of kinetic energy difference because the particles are moving faster. A liquid object has less thermal energy than a gas of the same energy. So if we take 100-degree water versus 100-degree steam, so the particles are closer together for the water, the liquid version, so they have less potential. The gas or steam, those particles are further apart, and so there's more potential there. So we'd say steam has more thermal energy than liquid water at 100 degrees. And this thermal energy can be transferred from a warmer object to a cooler object. Recall that transforming is when we change the type of energy, but transferring is when we keep the same type of energy, but it's going from one object to another. We can also transform this energy. So we'll learn about this soon, that steam turbines takes the thermal energy of the steam to turn into kinetic energy of the moving turbine. So these lessons are more referring to transfer of thermal energy. So temperature measures the average kinetic energy of all the particles within the substance. We cannot measure the total thermal energy of an object because it's impossible to measure every particle. So that's why it's an average EK. And we've got different temperature units, some that are not included here, but we will be using Celsius a lot. And this is based on a scale where water freezes at 0 and water boils at 100 degrees Celsius. And Kelvin, which is a set of units that a scientist would use, so there's scientific units, They're called Kelvin. We don't say degree kelvins, we just say Kelvin. So that's a scale where water freezes at 273 Kelvin and boils at 373 Kelvin. And you might wonder, why do we have different units? So if you have taken grade 11 chemistry, you understand that sometimes temperature is in the denominator of a calculation and you can't divide by 0. Kelvin is also, Celsius is important because it's based on water, important data point, physical properties of water, but Kelvin is important because if we bring the Kelvin temperature all the way down to 0 Kelvin, that is absolute 0. So that's the lowest temperature possible. At this point, atoms have no motion. And if it's equivalent to 0 Kelvin, if we take a look at it, well, if 0 degrees Celsius is 273 Kelvin and 100 degrees Celsius is equal to 373 Kelvin, you could see that the relationship is just that 273 units more for Kelvin than Celsius. So if you take the degree Celsius and add 273, you get Kelvin. If you have Kelvin, you subtract 273 to get degrees Celsius. So just for example, if we would say bromine boils at 58.8 degrees Celsius, determine this temperature in Kelvin. So Kelvin, in order to get Kelvin, we would add 273 units. So we would get 332 Kelvin. There is a very old series of animations, this video series called Eureka, which is, although it's old, the explanations are so clear, the animations are so cute, and there's nothing like it, so I always show these videos. Unfortunately, I will not be showing this video right here, right now, but I encourage you to watch the video and then come back to this point of the video. And in this video, just to kind of give you a rundown, but it is worth watching even after this summary of it. This little character is trying to heat up the swimming pools. The swimming pools are too cold to go in. So he has a cup, a small cup of 100 degrees Celsius water, or he has a big bucket of 50 degrees Celsius. And the question is, what's better for heating up the swimming pool? So the analogy that really works in this video is thinking of the teacup as $100 bills, a few $100 bills, whereas the big bucket of 50-degree water is like a whole bucket of $50 bills. So from the video, so you're going to watch the video. It's only a couple minutes, and it's very clear and worthwhile and so cute. So from the video, what does temperature depend on? So in the video, it explains that temperature is a degree of hotness. Temperature depends on the speed of the particles. And the degree of hotness, the analogy is the value of one bill. So the $50 bill or the $100 bill. So temperature depends on speed, but what does heat depend on? Heat is explained in the video as the amount of hotness. And so the heat depends on the quantity and the speed. So if you go back to the analogy, it's both the value of each bill and the number of bills to determine, would you rather have the value of money, the amount of money in the whole bucket or in the small teacup? Even though one bill in the teacup is $100 and one bill in the bucket is only $50, there is more total money in the bucket, or there's more total hotness in the bucket. And what was the heat used for in the video? It was used to warm up the relatively cold pool water. And to warm up something significantly, we need a lot of heat. So we'll need the particles to be much hotter than the stuff we're warming, and or we'll need a lot of those hot particles. So let's quantify heat. Talk about it a little bit more. So heat is the transfer of thermal energy. We use the symbol capital Q for heat, and Q is equal to delta E thermal. So the change in thermal energy is heat. This is analogous to our work energy principle. So work is equal to the delta EK. So this chapter's version of that is Q is equal to delta E thermal. Thermal energy is conserved in a closed system. So we're going to come back to that very important conservation statement in the next video. So note that heat is energy transferred from one thing to another. So it's a transfer of energy. They're at when the two objects are at different temperatures. Heat doesn't flow, even though we say heat flow and we know what is meant by that, but it's energy transferred. And the three methods of heat transfer, which you will have coming up in questions, we've got convection, conduction, and radiation. And you'll read more about those. So the factors that affect heat, we have the mass of the material. So it takes more heat to get a glass of cold tap water to warm up to 40 degrees than the amount of heat to take a whole bathtub of cold tap water to warm up to 40 degrees. So it makes sense that mass is a factor that affects heat. And we also have temperature change. So the greater the change required, the greater the heat energy required. So it's not about the temperature you start necessarily or the temperature you end at, it's both of them. It's how much temperature increase do you need or decrease do you need. So it takes more heat to warm up a cup of water by 50 degrees than it does to warm it up by only 10 degrees. And so it makes sense that temperature change is a factor that affects heat. And we also know that the type of material affects heat. Different substances reflect the thermal energy changes differently. So from the 2 cups in the photo, even if there's exactly the same mass and it needs to be heated by the exact same delta T, there will be more heat required for certain substances. So if this photo is water and oil, can you take a guess as to which one requires more energy? So if this is water and this is like vegetable oil, water requires much more energy for the same delta T as the oil. It will take more energy for 1 unit of water or 1 unit of mass to increase by 1 degree if that substance is water, because water has exceptional heat transfer properties considering that it's a liquid. And this property that we're going to get to is called specific heat capacity. So it does make sense that different materials heat up differently. If you touch different surface, let's say if it's a cold winter day, if you touch different surfaces, some of them actually feel much colder than they are than others. So if you touch a cold metal pole versus if you touch a brick wall or a plastic door, the metal handle of a door is feels a lot colder than the plastic door, even though they are at the same temperature. So it makes sense that the type of material is a factor that affects heat. If we put all of these factors, or these factors are all together in the formula for quantifying heat, Q equals mc delta T. So Q is heat in joules, it's a scalar quantity. M is mass of the material in kilograms. C is our new quantity that we're going to talk a lot more about, and it's called specific heat capacity. So this is a physical property. It's a constant for a substance at a certain state, and it's joules per kilogram Kelvin or joules per kilogram degrees Celsius. One thing that we did not stress when we took a look at the different temperature scales, because if you look at this formula, the slope is 1. If we increase degrees Celsius by 15 degrees, let's say, then it's an increase in 15 Kelvin. So that's not like with Fahrenheit. So if you visited another country and they measure their weather in degrees Fahrenheit, if from the morning to the evening, it increases by 10 degrees Celsius. It's not the same as 10 degrees Fahrenheit. So the delta T actually doesn't matter if we're using degrees Celsius or Kelvin. So just to go back, so Q equals MC delta T. It is important though that you'd watch that your units match. So often we're going to be doing problems where you're given grams and you often have to convert. And remember that a joule is a very small quantity. So often we'll report our answers in kilojoules in the back of the book, or in the question, it might be kilojoules. So remember that 1,000 joules is 1 kilojoule. I'll also note that on page 281 of your textbook, there are specific heat values. And because it's a material property, so if I tell you that this is vegetable oil or olive oil or mineral oil or something, if I tell you the substance and I tell you it's a liquid, there is a C value that goes with that substance that tells you how easily it heats up. So materials with very high specific heat capacity require a very large amount of energy to raise the temperature by 1 degree for 1 unit of mass. So if you look at the joules per kilogram degree Celsius, so for 1 kilogram to increase by 1 degree Celsius, it's a lot of joules. We also, I guess also as a result of the definition of specific heat capacity, I was speaking to, if you set the same amount of mass and the same delta T, then your energy is different. Excuse me. But also, if you have a set amount of energy, the amount of temperature increase you can accomplish depends on the specific heat capacity. So if you have a set amount of energy available for warming the water or warming the oil, a set amount of energy might have a very small temperature change for the water, but a very large temperature change for the oil. And having the high specific heat capacity of water, making it very difficult to change the temperature, we owe a lot of the hydrosphere and biosphere and a lot of ecosystems to this special property of water. So because water is in living creatures and in the environments that living things live in. So that's why you have winter starts, and even though the air is in the negatives, at the very beginning of winter, the lake doesn't immediately freeze. So it takes time for that heat transfer from the water in the lake to the air, for the lake to actually get to be so much energy that is removed that it can freeze. And then if you think about like the first time, I know it's hard to think about summer coming up so quickly, but if you think of the first day of the summer that you can go out into the water, the first day the water might still be cold because it takes a lot of energy from the sun to warm up the water in the lake as compared to how much time it takes for that sun in that same environment to heat up the land, the sand, or the rocks beside the water. So specific heat capacity of water is something that you're going to read about. So let's try an example. So how much heat energy is required to heat a 2.5 kilogram piece of copper pipe from 25 degrees Celsius to 66 degrees Celsius? So because we're told that it is copper and it's a heat transfer problem, we're going to want to have thermal properties of copper. So the first thermal property we're learning in this chapter is specific heat capacity, and we're going to find that on page 281. You'll need to know to look for it, since for the time of assessments, you'll be given the constants, but you need to know to look for them. So if we write out our givens, we have mass, we have initial temperature, we have final temperature, therefore we can find the delta T. We know the specific heat capacity of copper, And you notice it's joules per kilogram degree Celsius. So we are working with kilograms and we are working with degrees Celsius. So we're moving forward with compatible units. We want to know how much energy, how much heat energy, so that's Q, and we only know one equation for Q so far, Q equals MC delta T. You substitute in those givens, and we get 39,000 joules, or you can say 39 kilojoules if you would like. Part B says if the same amount of energy were applied to 1 kilogram, so 1 kilogram is less mass than 2.5 kilograms, what would be the temperature change? So if it's Q equals MC delta T, if we isolate for delta T, they said in the same amount of energy with less mass. So now we sub in less mass with the same amount of energy, we're going to get a larger delta T than in the original problem where we had 41 degrees. That makes sense. If you're heating up less, then that energy can go further in heating it up more. So we would conclude with two significant figures. You'd need to report with scientific notation 1.0 times 10 to the 2 degrees Celsius. And part C, what mass of copper would experience a temperature change of 70 degrees Celsius with this thermal energy? So what mass? We're solving for mass and we're given a delta T with this thermal energy. So it's still the same Q value from part A, but now we're going to rearrange to solve for M. So M is equal to Q over C delta T. Substitute in our givens, and we would get 1.464 kilograms, which rounds to 1 kilogram. Is it one significant figures? Yeah, because now we only have 70 degrees Celsius is only one significant figure. So A and B, you would round to two significant figures. Part C, you would round to one significant figure. And just a note to mention about these significant figures, you have to look to all of the measured numbers that you used at some point to solve a problem. So in this problem, in this chapter, we're going to have some constants. And you're going to look at the significant figures of those constants. Now, not very often. They're measured in a lab with great precision, so it's not very often that those significant figures will be the smallest limiting significant figures, but it's still worth a look. Also, it's all of the numbers that at some point were used to get this answer have to be considered. So if you look at the Q value from part A, well, 70 is only one significant figure. But if it wasn't 70, if it was 70.0, we would have to look to what was the calculation that gave us this Q value, and is there a smaller number of significant figures than what's already visible here? So just be aware of that. But for this one, it's only one significant figure, so 1 kilogram is our answer. Okay, so there is a really great video for you to watch. It's only a couple minutes long. And it goes over some misconceptions about temperature. And I would like you to watch it. So pause this video right now, go to that video at the end of this, and come back to this spot. And basically the message here, it's a misconception for a reason. So you might be scratching your head at first, but don't worry. It's something that it is a common misconception, and we do have to figure this out for this chapter. So it's really worth going to this video. So the gist of it is that when we feel temperature with our hand, we're really detecting how quickly thermal energy is being removed. So whenever we're sensing a temperature without using a thermometer, but we're like touching it, we're actually detecting how quickly thermal energy moves. So in the person's hand, at first they put a plastic block and a metal block, and the metal block obviously feels colder. He measures the temperature of both, and they're actually the same temperature. But why does the metal feel colder? It's because the metal of the block is sucking the thermal energy out of your hand very quickly, and your hand sends the message to your brain that it must be pretty cold in front of your hand because something is removing energy very quickly. And it comes down to that metal has a lower specific heat capacity. So there's a big change in temperature for a little amount of energy moved. Then they say, all of these people he interviews say, oh yeah, the metal feels colder. Then wouldn't you expect that ice would take longer to melt on something that's colder? But he puts ice on the metal and then ice on the plastic, and the ice melts faster on the metal. And it again comes down to that the cold in the metal is being sucked into this ice cube more quickly to provide the energy required to melt it. So I guess the reasoning of all of that he does is that the specific heat capacity of the metal is low. And the point of showing it to you is to remind you that when you feel temperature with your hand, you're really detecting how quickly the thermal energy is being removed or added. Okay, we've come to a really important principle, and it is that principle of thermal energy exchange. It's also called the principle of heat exchange. It states that when a warmer object comes in contact with a cooler object, the warmer object loses heat and the cooler object gains heat. And the amount of energy lost by the warm object equals the amount of energy gained by the cold object. So if we say the warm object loses Q released and the cooler object gains Q absorbed, Q released plus Q absorbed equals 0 joules. Or they're equal in magnitude, but opposite in sign. So they're scalar values. They don't have a direction, but they can be positive or negative. Q released, if temperature is going down, delta T is negative. So Q released is going to be the negative one. So negative 55 joules plus positive 55 joules equals 0 joules. So let's try an example. Oh, this is Mrs. Teapot from my goddaughter's favorite movie, Beauty and the Beast. So that might be a good exit ticket question for you there. What's his name? I don't remember. Okay, example 3. A 0.5 kilogram pot of hot water for tea has been cooled to 40 degrees Celsius. How much freshly boiled water must be added at 100 degrees Celsius to raise the temperature of the tea water to a respectable 65 degrees Celsius? So, I don't know, we're tea snobs here, and we need to drink our tea at 65 degrees Celsius. But when you boil water, you get it at 100 degrees. Isn't that so annoying that you boil hot water and then it's not ready to drink right away? You have to wait for it to cool. Anyways, we're not going to wait. We're going to add a little bit of cold water. So we want, this is a different problem than I was thinking. So our pot of hot water for tea has cooled to 40 degrees. So that's too cold. We're really tea snobs here. So we just don't want like bath water temperature. We want 65 degrees Celsius. So let's draw a diagram. It's really important in these to draw a diagram to organize all the givens because it might be overwhelming right now. There's so many givens. So I'm going to draw a container. It's not going to be a teapot because I cannot draw. But we're going to fill up this beaker with the mass of our cold, our 0.5 kilogram water that's too cold. It's 40 degrees Celsius. Nobody drinks tea at 40 degrees. So we want to bring that up to a final temperature of 65 degrees Celsius. On top of that relatively cold water, we're going to put the hot water. So we'll call that M hot. We want to know how much of that hot substance, that's the hot side, do we need to add if that hot water is 100 degrees Celsius. So we know the degree of hotness of the cold side, and we know the degree of hotness of the hot side. We know the amount of the cold side. We want to know the amount of the hot side. We know that both of them together, once mixed, will give us 65 degrees Celsius. So the hot side and the cold side are always connected by TF. Remember that delta is final minus initial, so delta T is TF minus TI. If we sort of graph what's going to happen over time, we have the 40-degree water, and as soon as we mix, it's going to increase up to 65 degrees Celsius. At first, it's going to change its temperature per second very quickly, and then it's going to change, it's going to warm up more slowly. At first, it's warming up really quickly because it's a sudden exposure to hot, and then it's going to slow down. Then we have 100 degrees C hot water that we're going to add on top of it. 100 degrees C water, it very quickly cools down, and then it's going to taper off. But both of them, if you can fast forward to infinity, so it never truly gets there, but infinity, then they will both be at 65 degrees Celsius. So this here, this from here to here, that is how much energy is gained. That is Q cold. Q cold is going to gain that much energy. Q hot is going to lose that much energy. And so question right now, do they meet in the middle? So what's the middle? 40 plus 100 equals divided by 2. That's 70. So we are more on the cold side at the end than the hot side. So that's something worth noting. So imagine if, so the hot has a bigger effect. No, sorry, the cold has a bigger effect. So if we have, imagine if you have a big bucket of cold and you add just one drop of hot, then this curve is just going to be like that. It's going to barely move. So the fact that this 65 degrees is more on the cold side means that my M cold is bigger than the answer that I'm getting for M hot. So what am I talking about? I'm setting up your expectation for your common sense check. I am expecting that M hot will be smaller than 0.5 kilograms. So keep that in mind. We set up these problems kind of similar to conservation of energy because it is a form of conserving the energy. We're saying we're saying all energy is accounted for. The energy that is lost by the hot side plus the energy that is gained by the cold side equals 0. So rearrange that. We get Q hot equals negative Q cold. Now, it doesn't matter if you wrote negative Q hot equals positive Q cold. I get that question a lot, and it doesn't matter. In this way, we have Q cold is going to be negative, so double negative is going to be positive. And then Q hot equals Q cold, MC delta T both sides. And I guess I will give you this little trick, is that negative is critical if you're solving for any of the temperatures. But if you're not solving for the temperatures, it turns out it works itself out. We rearrange for M hot because we have C hot. We have, well, I guess, this is something worth mentioning. Do we have the specific heat capacities of both sides? All you need to know is the substance and have a table nearby. So this is water on the bottom and water on the top. It turns out that they both have a specific heat capacity of 4,180 joules per kilogram degree Celsius. That's a very high specific heat capacity, but it is water. So it actually cancels out both sides. So we don't actually need to know it in this special case where they're both water. If the masses were the same, you could cancel them out, but they're not. So M hot equals negative M cold delta T cold over delta T hot. Remember that the delta T cold is, final minus initial. This is going to be positive, and final minus initial, this is going to be negative. So the negative divided by the negative, it becomes positive. So we substitute in our values that were given, and we get 0.357 kilograms. And because there was only one significant figure in 2 of the temperatures, we only round it to one significant figure. So the correct answer is 0.4 kilograms. Okay, now it's time for you to do some practice problems. I want you to do these problems and then really study them because I've cut out some of the problems and I want you to focus on the ones that are really important. So please make sure that you submit the exit ticket for topic C5 and do these problems and then submit them under the practice problem section. Have a great day. Stay safe and be well.